In this lesson, we'll begin by introducing a new model to describe the electric field surrounding a charge distribution, called the electric field line model, or sometimes called the line of force model. From there, we'll take a slight detour and discuss the motion of a charged particle in an electric field. We'll see how the physics for a charged particle moving in an electric field is extremely similar to a situation you're already very familiar with, namely that of a mass moving in a uniform gravitational field, what we call a projectile. And we'll conclude today's lesson by introducing this all-important concept called the flux of a field, in our case, the flux of an electric field. Certainly later in the course, we'll talk about the flux of a magnetic field. Our discussion of the flux of the electric field will lead us to a fundamental law of electromagnetism called Gauss's law. We'll derive Gauss's law in this lesson, and then we'll spend the next lesson learning how to apply Gauss's law to determine the shape of the electric field around a charge distribution. We know that the electric field surrounding a charge distribution is a vector field. That is, at every point in space surrounding the charge distribution, we can represent the electric field with a vector, having both a magnitude and direction. Now, the task of drawing little arrows at gazillions of points in space to represent these electric field vectors is quite time-consuming. So we're going to discuss another model for representing the electric field, that will give us the same information as the vector field model, but will require much less time to describe. This model involves what we call electric field lines as opposed to electric field vectors, and is often called the line of force model as opposed to the field model. So, what is an electric field line? An electric field line is a continuous curve showing the direction of the electric field at various points in space. Remember that the direction of the electric field at a given point in space surrounding a charge distribution is the same as the direction of the force on a positive test charge that is placed at that point in space. As we're saying previously, drawing electric field vectors at every point in space is quite time-consuming, if not impossible. So, this electric field line model, as we're saying, will provide us with the same information as the electric field vector model, but is going to require much less time to construct, as we shall soon see. Let's now take a look at a specific example of a charge distribution and then compare the vector field model with the field line model, what we call the line of force model. The example we'll consider is that of a spherical positive charge distribution. And you'll notice here that we look at a spherical positive charge, big Q. Notice that for the electric field vector model, we can draw a vector to represent the electric field surrounding this positive charge Q at each point in space. We certainly can't draw all of the field vectors. That would take an infinite amount of time, but we draw enough electric field vectors to get an idea of both the field magnitude and direction. Note that the direction of the field at any point in space is radially outward, consistent with the requirement that the direction of the electric field is the same as a direction that a positive test charge would experience, the force it would experience at that particular point in space. Also notice that the field gets weaker with distance, consistent with the inverse square law nature of the Coulomb force and field. We produced the electric field line model, the line of force model, simply by drawing the continuous curves connecting the various field vectors. You can see how much less time it takes to draw the field lines versus the field vectors. In the next slide, we'll see how we can get the same information from the field line model that we can get from the vector field model. So from the previous slide, I think it's pretty apparent that the electric field line model clearly shows the direction of the electric field in the same way that the electric field vector model does. But how do we get information about the magnitude of the field from the field line model? Well, in this slide, we will start to see. But let's first begin by discussing the direction of the electric field given the electric field line model. So we can say that electric field lines are represented by arrows that start on positive charges and end on negative charges. In this way, we see that the direction of the electric field line, okay, at a given point in space can be defined exactly the same way as the direction of an electric field vector at that point in space. Okay, namely, we look at the direction of the force on a positive test charge at that point in space. So we can also say that the electric field vector is tangent to the electric field line at each point in space. So from a field line model, okay, if we have an electric field line, what I'm showing you here in red, we can determine the direction of the electric field at any given point in space, let's say right here, okay, by first drawing in the tangent line to the field line and subsequently drawing the electric field vector along the tangent line, okay, in the same direction as the field line. So in this case here, we see that, okay, this electric field vector, this arrow I'm showing you here is tangent to the field line at that point in space, and it is consistent with the direction of the electric field line. Now, as far as the magnitude of that electric field vector, okay, we will discuss that shortly. So, it's now shortly. Let's take a look. How do we get information about the magnitude of the electric field using this field line model? Okay, in the field line model, we assume that the number of field lines beginning or ending on a charge is proportional to the magnitude of the charge. So how many field lines you actually choose to draw for a given amount of charge is up to you. But you need to define some sort of scale and then be consistent in using it. So for example, if you draw a given number of field lines, say 10 field lines, okay, which emanate from a charge Q, okay, if you were to double the amount of charge to 2Q, you would then need to double the number of field lines emanating from it in order to be consistent, okay, with this criteria here. So it also turns out that the number of field lines, and this is the new part, and this is the part that is probably the most conceptually difficult to visualize here. Okay, but we will get some practice when we can visualize it for some real charge distributions in some future slides. We're saying here that the number of field lines per unit area through a surface perpendicular to the field lines, this is what we call the field line density. Okay, the number of field lines per unit area, that is the number of field lines, okay, penetrating a surface, okay, divided by that surface area. Okay, that the field line density is directly proportional to the magnitude of the electric field in that region. To say this qualitatively is much simpler. We can say that the electric field is large, okay, where the field line density is large. In other words, the magnitude of the electric field is large, okay, in a region where the field lines are close together, and the magnitude of the electric field is small in a region where the electric field lines are far apart. Okay, so we can see that the field line density tells us something about the magnitude of the electric field. Okay, and like I said, we will take a look at this in greater detail when we look at some specific examples. And lastly, we'll say that electric field lines can never cross one another, since this would indicate that the electric field would have two directions at a single point in space. And this would clearly contradict the notion that the electric field is a continuous field. It cannot have two different directions at a single point in space.
So we'll start the simulation with a single point charge of 2 microcoulombs. So remember that the direction of the electric field is determined by the direction of the force on a positive test charge. So to see this, we're going to start by adding some positive test charges near our charge distribution to see in which way they move. So let's create some test charges here. We're going to place them around this single point charge, and you can see that they move radially outwards in time, indicating the radial dependence of the Coulomb force. Next, we're going to place some electric field vectors around the charge distribution. So we're going to place them at various locations here. And I want to place enough of these here so that you notice the pattern here. So note the inverse square law nature of the electric field, first of all, that it gets weaker as the square of distance. So as we move radially further away from our positive test charge, we see that the magnitude of these electric field vectors decrease in time. Also note the radial dependence of the electric field, that the field points in the radial direction, in this case outwards because it's a positive test charge, at all points. Next, we're going to add in some field lines, and these field lines will represent our line of force model. Want to just point out here that with this simulation, this unfortunately does not show us the direction of the electric field, but one of the things it does nicely show is that the electric field vector is tangent to the electric field line at any given point in space, so it does nicely show that. So I'm going to use this equipotential button here. I'm gonna clear our electric field vectors here. I'm going to use this equipotential button here just to show you just to create two circles here so that we can look at something else in this field line model. Notice that these two circles, the pink circle and the blue circle, have different radii. Notice that the field line density, which measures the number of field lines per unit area through a surface that is perpendicular to the field lines, notice that this field line density decreases as we move radially outwards. So if I'm looking here at this pink circle here, notice that these field lines where the cursor is are perpendicular to the surface here, and you'll notice that we end up with two field lines passing through a surface of this small area here. Notice as we move further away here, as the radius gets bigger, we still have two field lines, but notice how much bigger the blue surface is out here. That is, this portion of the circle is, compared to the pink portion in here. This tells us that out here, further away from the charge distribution, the field line density is much smaller, suggesting that the electric field is much weaker there. So this is how we get information about the strength of the electric field using the field line or line of force model. Remember that it is the field line density that tells us something about this field strength. One more thing you should notice that the field lines never cross one another. suggesting that the field is continuous at all points in space. All right, so we're going to switch simulation software here because this piece of software will actually show us the direction of the electric field lines for a given charge distribution. So we'll start once again with a single point charge. Okay, let's say with a charge of, +1. So you see the red charge on the left having a charge of +1. Which is positive. Notice once again that the field lines leave or move away from the point charge consistent with the direction of the electric field. Also notice that the simulation uses 10 field lines to represent a charge of +1 charge units. Let's now switch the sign of the point charge and see what happens to the field lines. So here we're going to go from 1 to -1, and you now see that the field lines point radially inwards as opposed to radially outwards. Our field line model requires that the electric field lines move away from positive charges and move towards negative charges. Notice what happens if we now double the amount of charge. I'm going to go from -1 charge units to -2. So when we double the amount of charge, we double the number of field lines from 10 to 20, consistent with the requirement that the number of field lines is directly proportional to the amount of charge. Now let's take a look at a charge distribution consisting of 2-point charges. So we'll start by considering the special case of the electric dipole. So we'll make our charge on the left here with a charge of +1 charge units, and we'll put our charge on the right, this black charge, with a charge of -1 charge units. So notice that the 10 field lines leave the red positive charge on the left, and the 10 field lines now enter the negative charge on the right. This is consistent with our field line model, which requires that the number of field lines entering or leaving a charge is proportional to the amount of charge.
So let's very briefly review some of the main features or conclusions from the two simulations that we just witnessed. Okay, we'll look at how certain changes we made in the simulation will affect the field line model as well as the electric field vectors themselves. So starting with what happened when we changed the magnitude of the charge of our spherical charge distribution? What effect did this have upon our field line model? Well, we saw that when we changed the magnitude of the charge, this changed the number of field lines that either entered or exited the charge, but did not change the direction of the field lines. So certainly twice as much charge means twice as many field lines, okay, either entering or leaving the charge, depending on the sign of the charge. What effect did changing the magnitude of the charge have upon the electric field? Well, certainly it changed the magnitude of the electric field, okay, at every point in space. Now, when we changed the sign of the charge of our charge distribution, what effect did that have on the field line model? Well, this changed the direction of the field lines, but not the number of field lines. Okay, remember that according to our model, we say that field lines always leave positive charges and enter negative charges. Okay, so this would certainly, changing the sign of the charge would certainly change the direction of the field lines. And of course, we know that changing the sign of the charge of our charge distribution will cause the direction of the electric field to change at any given point in space. What happened when we moved radially away from our spherical charge distribution? In other words, when we moved the pointer in the simulation radially outward along the field line. Well, we saw that, okay, as we did so, as you move away from the spherical charge distribution, you saw that the field lines get further apart. In other words, the field line density decreased. What did this signify about the electric field? This tells us that the magnitude or strength of the electric field becomes weaker as the field lines get further apart. So remember that it's the field line density that gives us information about the strength of the electric field at a given region in space. And finally, when we move the pointer in the simulation at a fixed radius, we saw that the field lines maintained a fixed spacing, meaning that for a fixed radius, okay, for a spherical charge distribution, the field line density remained constant, telling us that the strength of the electric field remained constant for a given radius. So are electric fields, and thus the field lines representing them, are they imaginary or do they really exist? In the demos that follow, we're going to take a look at some charge configurations and see the electric field is indeed a real entity. Okay, for each of these configurations, we're going to apply a Wimshurst generator to two neutral conductors. Okay, this will have the effect of giving each conductor an equal yet opposite charge. The electric field that gets established in the space surrounding the charged conductors will interact with little plastic grains suspended in oil, causing them to reveal the shape of the electric field. So we can infer that in regions where the grains are close together, the field line density is large, suggesting that the field is strong there. Okay, of course, the little plastic grains can't show us anything about the direction of the field. We have to add in the direction of the field lines from our knowledge of which conductor is actually positively charged and which one is negatively charged. So using our field line model, we should have as many field lines leaving a positively charged conductor as entering a negatively charged conductor, since each of these conductors is equally charged, right? Same magnitude of charge for each ones. So we will start in the next slide by taking a look at the parallel plate capacitor, okay, and trying to answer this question. Can we see any evidence of an electric field that is being established in the region between these two charged conductors? So I'll admit that the shape of the electric field was, admittedly somewhat less than clear, but hopefully you started to see some of the field lines form, perpendicular to the conducting plates themselves. In the next slide, we'll take a look at the electric field surrounding the electric dipole. And once again, a little imagination certainly helps you see the form of the electric field surrounding these two equal but oppositely charged spherical conductors. Okay, this is the dipole field. So let's now check out the combination of a spherical conductor, okay, with that of an equal but oppositely charged plate-like conductor. So the shape of the field is clear as mud. I think we can at least agree that there is certainly evidence to suggest that a field exists in the region, okay, surrounding these conductors, even though the shape of the field is not so transparent. So let's take a look at one more charge configuration. Okay, and this is supposed to simulate a cylindrical capacitor, okay, where we have two equal but oppositely charged cylindrical conductors. Saving the best for last. I thought that the shape of the electric field was much clearer for this last charge configuration. And I just want to point out, now that we've seen all of them, that for all of these equal but oppositely charged conductors, when we are drawing in the electric field lines, okay, to represent the electric field surrounding these conductors, notice that we must draw the same number of field lines leaving the positively charged conductor as entering the negatively charged conductor, since both of these conductors had the same magnitude of charge. And as we say, you couldn't tell from the simulation, but we always draw electric field lines leaving the positively charged object, okay, and entering the negatively charged object. So in this slide, we'll look at a few more examples to gain some practice applying the electric field line model, that is a line of force model, to some specific charge configurations. And we're told in the problem that a charge having a magnitude Q should be represented by 8 field lines. So we'll start by taking a look at a spherical charge distribution having a uniform charge density, okay, total charge of plus Q. So here we have it. We need 8 field lines, and because it's a positive charge and we know that field lines leave positive charges, okay, we can represent the field line model like this. You'll notice that these field lines are symmetrically distributed in space, suggesting that for a given radius, the field line density would be constant, right? The number of field lines per unit area would be constant for this spherically symmetric charge distribution. And you notice here that as you go radially outward, the field line density decreases, suggesting that the field gets weaker. If we wanted to double the charge and draw the field line model for a charge distribution with twice as much charge, well, we said if 8 field lines are needed to represent a charge of plus Q, we need twice that many, or 16 field lines, to represent a charge of plus 2Q. Once again, these field lines point away from the positive charge. Notice again their uniform distribution in space. we are asked here in the third part here for the +2 charge distribution to identify regions where the electric field is both strong and weak. And let me grab a laser pointer here. And you'll notice here that when we are close to the charge distribution, if I look at this area here, we see that the field lines are fairly close together, suggesting a strong field. Compare that to a bigger radius out here. You'll notice that the field lines out in this region are spread further apart, okay, suggesting that the electric field is weaker in that region. So remember that the field line density, that is the number of field lines, okay, per area, tells us something about the strength of the field. And lastly, if we look at a charge of -q, again, a charge having a magnitude of q is represented by 8 field lines, but a charge of -q suggests that, okay, the field lines are going to, end on a negative charge distribution here. So the field lines point towards this charge of -q. Once again, they are uniformly spread out in space, suggesting that the field line density is uniform, okay, for a given radius, right? It's a constant field line density in a given radius. In the previous slide, all of the examples we considered consisted of single charges. In this slide, we'll look at examples consisting of 2 charges separated by a small distance, starting with a case of 2 like positive charges. So drawing the electric field lines surrounding these charges, remember that a charge having a magnitude q is represented by 8 field lines. Both of these are positive, so we need to have 8 field lines leaving both of these charges. The spherical symmetry of each of these charges suggests that, okay, there will be this radial dependence, okay, to the field lines. Remember that when you're trying to determine the direction of a field line in space, okay, the direction using the field line model is equally applicable to how you would find the direction of the electric field at a point in space using the electric field vector model. That is, take a look at placing a positive test charge, a small positive charge at that point in space, and determining the direction of the force on that test charge. The direction of the force on that small positive test charge will indicate the direction of either the electric field vector or the electric field line at that point in space. If we now take a look at what we would call the electric dipole, a very important charge configuration, this consists of 2 equal but opposite charges separated by a small distance. So once again, a charge q represented by 8 field lines. 8 field lines must leave the positive charge, but for a charge -q, 8 field lines must enter it. Okay, we can represent the electric field line model as such. You'll notice that not all of these field lines are continuous. That is simply because of a lack of space. We have to infer that, okay, these field lines would connect, given that these are the only charges that exist, okay, in this case. We're asked in the second part of this question, drawing the electric field vectors at the points indicated. So for certain points in space, I'm going to draw these 3 electric field vectors. Note that according to our model, the electric field vector is tangent to the field line at that point in space where you're trying to draw the field vector. Okay. Also notice that the direction of the electric field vector is identical or in the same direction as the electric field line at that point in space. In our last example, we'll consider having 2 charges that are opposite, okay, but not equal, separated by a small distance. So here the charge +q, as we've said many times, should be represented by 8 field lines leaving it. The charge -q/2, which has only half the magnitude, should have half as many field lines, in this case entering it because it's negative. So we should have 4 field lines entering it. Notice that this charge configuration here fits the bill. Okay, notice that the 4 field lines that leave the charge +q and enter the charge -q/2, okay, those field lines have definite beginnings and endings. The 4 other field lines leaving the charge +q cannot enter the charge minus q over 2. Given that these are the only two charges that exist in the entire universe, those field lines will travel forever, okay, outwards, and will not land on any other charges. So in this slide and the next several slides, we're going to digress from our discussion of this new electric field line model, this line of force model, and now turn our attention to the effect of an electric field on a charged particle, really a uniform electric field acting upon a charged particle. Now, we know that if a charged particle exists in a region of space with an electric field, it will experience a force from the field. And from our understanding of classical mechanics, okay, we know that the motion of the particle will be affected by this force. Okay, now, as we said in the introductory slide of this lecture, our understanding of how a mass in a gravitational field moves in response to a gravitational force, whether in the one-dimensional case of a falling body or the two-dimensional case of a projectile, this understanding is completely analogous, okay, to the physics of a charged particle moving in a uniform electric field, as we shall soon see. So, keeping this analogy in mind, we'll see that there's really not much new learning that's going to take place here. Okay, you already know the physics. Our understanding of the kinematics of falling bodies and of projectile motion is all that we really need to be able to understand what happens to a charged particle that moves in a uniform electric field. So let's start by making the side-by-side comparison between, okay, the mass, particle with mass, and the particle with charge. And we will start by looking at a mass, let's say little m, near the surface of the Earth, where we consider that mass to be in a uniform gravitational field G. We know that, okay, for such a mass in a uniform gravitational field, like what an object with mass would experience near the Earth's surface, okay, that it would experience a force, okay, given by the weight of the mass here, the mass times the acceleration of gravity. In a similar way, okay, we can say that if you have a charge, a particle with a charge q that exists in a uniform electric field, it too is going to experience an electrostatic force, okay, given by this expression, okay, the charge of the particle times the electric field. Remember, this is how we define the electric field. Okay, so this is nothing more than the definition of the electric field. And we can think of this perhaps as a charged particle that is placed in between the plates, the charged plates of a parallel plate capacitor. Parallel plate capacitor consists of two conducting plates that are parallel to each other that have equal and opposite charges. Okay, and this would be a charge configuration that would set up a uniform electric field in the region between the plates. So you'll notice in the diagram here we have a charged particle Q, okay, placed in this region, and it too is going to experience a force given by Q times E. Now, one of the differences between a mass in a gravitational field and a charged particle in an electric field is that there's only one type of mass, and therefore only one direction that that force on the mass can have. Whereas for the case of a charged particle, because charge comes in two types, okay, we could have a positive charge or negative charge, that tells us that the force on that charged particle, while being in one dimension, okay, really has two possible directions, unlike the case of the mass in the gravitational field. When we apply Newton's second law to determine the acceleration of either the mass or the charged particle, okay, we see here that on the left-hand side of Newton's second law, the net force acting on our mass here is just its weight, mg. Set that equal to the mass times the acceleration, and we come up with this fairly obvious conclusion that the acceleration of that charged particle is simply g. Okay, and this vector g, when we're talking about a gravitational field near the surface of the Earth, it has a magnitude of about 9.8 meters per second squared, and of course it has a direction that is always downwards towards the center of the Earth. For the case of the charged particle in the uniform electric field, okay, once again applying Newton's second law, the force on that charged particle is given by Q times Z. Notice that that gives a possibility of two different directions, right? Because Q can be both positive or negative. The electric field has a given direction, but okay, when you multiply it by charge with two possibilities, you get two possibilities for the direction of that resulting force. Setting that equal to the mass times the acceleration, okay, and solving for acceleration, we get this slightly more complicated expression here that the acceleration of the charged particle in the uniform electric field is given by the charge, okay, which also has a sign, right? Don't forget, it could be plus or minus times the electric field divided by the mass. So, when it comes to describing the resulting motion of either a mass released at rest, okay, in a uniform gravitational field, or a charged particle released from rest in a uniform electric field, remember that the kinematic equations describing motion for constant acceleration are alive and well. And when you look at our accelerations, whether for the mass in the gravitational field or for the charged particle in the electric field, both of these accelerations are constant. Therefore, those kinematic equations apply. So starting with the case of the mass in the gravitational field, the linear motion must be in the direction of the gravitational field g, since there's only one type of mass. The kinematic equations of motion apply. Okay, let's just quickly restate those here. All right, I won't read them to you. You know these by heart, okay, by now I'm sure. What we will do, though, is these four kinematic equations of motion, we will take a look at the special case. If they're released from rest, we can assume that the initial velocity is 0. We can also assume that the constant acceleration is, okay, whatever g, the gravitational field strength would be. And these four kinematic equations give the three interesting results here. The first one, this tells us the position of the mass, okay, at any given time, right? Okay, position, in this case, the displacement delta y is a function of time. That's the equation of motion for this mass. Okay, we also have an expression that tells us the velocity of that mass at any time. And then finally, we can relate, okay, the first two and find an expression for the velocity related to position. When it comes to the motion of the charged particle in the uniform electric field, which is released from rest, okay, in this case here, we also have linear motion, okay, the acceleration is constant. Notice that the charged particle will move in the same direction as the electric field when the charge is positive, but it will move opposite the direction of the electric field when the charge is negative. So we have the two possible directions of motion, unlike for the case of the gravitational field. Okay, those kinematic equations are alive and well. They apply because the acceleration is constant. Okay, plugging in the specific initial conditions here. Okay, for a particle released from rest, once again, the initial velocity is 0. That constant acceleration, okay, QE over m, which we came up with the okay, expression above. So when we see how this affects the kinematic equations here, this first equation gives us a position as a function of time. That's the equation of motion. If you want to know where will that charged particle be in this uniform electric field at any time, this is the expression that would give it to you. Second expression gives us the velocity as a function of time. Okay, how fast, okay, will that particle be moving at a given time? And finally, once again, our last equation will relate the velocity to the position rather than the time. Okay, and we can use this equation to tell us, okay, the velocity of a particle, okay, of a charged particle in a uniform electric field at some certain position. We now turn our attention to the more general case where a charged particle could move in 2 dimensions in a uniform electric field. And to understand this, we'll start with what we already know, which is the case of the classic projectile. That is for a mass which is projected into a uniform gravitational field. We'll look at the simplest case here where the mass is projected horizontally at a constant velocity, okay, in a gravitational field which is perpendicular to it. And if we want to look at it, the more complicated case where the mass is not projected horizontally, you recall we had to break up that velocity into both its horizontal and vertical components. Okay, it complicated things slightly, but not that much. So we can say that for that case, where you have a uniform field and you have a particle moving with a constant velocity, okay, that has at least a component perpendicular to that field, the trajectory of the particle is going to be parabolic. So we know that the classic projectile, the path, is parabolic in nature. So here we can show that schematically here. Because whether the particle is released from rest in the gravitational field or it's projected in the gravitational field, because the gravitational field is constant and thus the acceleration is constant, the kinematic equations of motion apply. So here recall that the horizontal motion, which is uniform motion, is described very simply, okay, with this equation. Because there's no acceleration, we can simply say the horizontal displacement is just equal to the velocity times the time. For the vertical motion, for the projectile which has no initial velocity in the vertical direction, okay, then the equation of motion describing the position of the mass as a function of time is very simply given by, okay, delta y being 1/2 gt squared. The final velocity of the particle in the y direction is simply the acceleration, the constant acceleration times the time. In the x direction, remember that the velocity is constant. So whatever that initial velocity is, that will be the same as the final velocity. And in all cases here, okay, because we have a uniform field, the trajectory will be parabolic in nature. The same applies to the case of a charged particle which is projected into a uniform electric field. We will look at the simplified case where the particle is projected horizontally, okay, and the field direction is perpendicular to that. Things are only slightly more complicated here because we have really 2 types of charge. The charge could be either positive or negative. And unlike the case of the gravitational field, an electric field could be up or down. Whereas when we talk about a gravitational field, it was always downwards towards the center of the Earth. So I'm showing you one particular scenario here. This is the scenario where an electric field is directed upwards, the particle is projected horizontally, and that particle, that charged particle, is negative. In that case, okay, the trajectory, the parabolic trajectory, will be downwards. Again, the equations of motion come from our 4 kinematic equations where the acceleration is constant and they are valid. So you see here that for the horizontal motion, it's identical to that of the projectile. For the vertical motion, okay, the acceleration, the expression for the acceleration is slightly a little more complicated, but delta y equals initial velocity times time. There is no initial velocity when it's projected horizontally, no initial velocity in the vertical direction. That term goes to 0, and we've got 1/2 the acceleration times the time squared. So when you plug in our expression up here, okay, for acceleration, okay, you end up with this expression for the equation of motion. Likewise, the velocity in the vertical direction is simply the acceleration times the time. Okay, in which case here, we have really 2 components to the velocity, right? The velocity in the vertical or y direction is given by this expression. The velocity in the x direction is constant. So here we see that when you're solving problems here for charged particles moving in uniform electric fields, remember that you already know the physics here. Everything is completely analogous to the case of the mass moving in a gravitational field. In this slide, we'll take a look at a particularly simple example of a charged particle moving in a uniform electric field, and look particularly at a piece of technology which is becoming more and more obsolete as time progresses, and that is the cathode ray tube. The cathode ray tube used to be what all TV sets and computer screens were made out of until the last 15 years or so. The cathode ray tube, it's a vacuum tube in which a beam of electrons is first accelerated, then deflected under the influence of electric and/or magnetic fields. So we're asked in this problem to find out the electric field strength required to accelerate electrons in a TV tube from rest to 1/10 of the speed of light in a distance of about 5 centimeters. So how strong of an electric field do you need to have in this device to be able to cause this pretty immense acceleration, okay, for these electrons? So as we were saying in the previous slide, when we're talking about a uniform electric field, we're talking about a constant acceleration, which means the kinematic equations are valid. So as with any kinematics problem, we start by trying to identify what kind of kinematic information are we given in the problem, what is it we're trying to find. So in this case here, note that we've got a one-dimensional motion problem as opposed to a two-dimensional motion problem, okay, where here's a single electron, and as we know very well, we need to define a coordinate system, okay, to describe direction here. Since it's a one-dimensional problem, we'll use a one-dimensional coordinate system or number line. I'm going to arbitrarily choose motion to the right as being positive. So in this case here, what do we know? Well, we're told that these electrons start from rest. We are told that they need to reach a speed, okay, 1/10 the speed of light. Okay, so the speed of light is 3 times 10 to the 8th meters per second. Divide that by 10, you get 3 times 10 to the 7th meters per second. In a distance, this acceleration distance is 5 centimeters or 0.05 meters. Now, what we're trying to find here ultimately is the electric field strength, but we have an expression for that in terms of the acceleration. So we need to start by finding the constant acceleration. And we know very well we've got to choose the correct kinematic equation, right? All those kinematic equations contain 4 variables, 3 of which are known, 1 is unknown. So there's one kinematic equation that contains these 3 knowns and 1 unknown. It looks like this. We need to solve the kinematic equation for the desired unknown, which is the acceleration. So we plug in the numbers and do the number crunching, and we come out with an acceleration of 9 times 10 to the 15th meters per second squared. Remember that the electric field is related to the acceleration, okay, and we derived this expression on, okay, a couple slides ago, right? This is simply a statement of Newton's second law, okay, where we showed that the force on the electron, Q times E, was equal to the mass times the acceleration. Solve it for acceleration. This is what we come up with, and we're ultimately asked to find the electric field, so we can then solve the expression for the electric field. Okay, and when we plug in the numbers here, the mass of the electron, which if you don't know it, learn it. Okay, it's a very common charged particle used in these physics problems. Plug in the mass of the electron, the acceleration of the electron, which we found, and of course the charge of the electron, again a fundamental constant that you're going to need to know in this course here. And when we do the number crunching, we come up with an electric field strength of, okay, 5.1 times 10 to the 4th newtons per coulomb, okay, about 51 kilonewtons per coulomb. We now introduce this very important concept in electromagnetism known as flux, or more specifically, the flux of a field. Since we're talking about electric fields in this unit, we'll be talking about electric flux. But you should know that the flux concept applies to all fields. So what we learn about the flux of the electric field in this unit can be applied to the flux of a magnetic field in later lessons. So the flux concept. Definition of flux, and this is a qualitative definition only. We'll use a symbol capital Phi, that Greek symbol, to represent flux. Qualitatively speaking, we can think of the flux as a measure of the number of field lines, which we can think of as the amount of field that penetrates a given surface. So when we talk about the flux of a field, we're talking about a field that is penetrating some type of surface. And how much field penetrates that surface is a measure of the flux of the field. So because flux measures a number of field lines or the amount of something, it should make sense that it's a scalar as opposed to a vector quantity. What sort of factors affect the flux of a field? Well, it turns out there's three, and we'll try to take a look at each of those factors with a simulation here. Starting with the area of a surface. If we said that we always talk about the flux of a field through a surface, okay, let's take a look at a uniform field. It could be an electric field or any field for that matter. Let's take a look at a surface that has an area given by this red rectangle here versus the flux through this green surface, which is represented by a much greater area. I think it's pretty easy to see here that the greater the area of the surface, okay, the greater the number of field lines that penetrate the surface, therefore the greater the flux through the surface. So in essence, we can say that there's a direct relationship between the flux through a surface and the surface area of that surface. What about the field strength itself? Well, to see that, let's take a look at two fields. Okay, here's a relatively weak field, uniform field. Here's a much stronger uniform field. Let's consider a single surface, same area, run a little controlled experiment here, and take a look at how does the field strength affect the flux through that surface. Well, I think it's pretty easy to see that when you look at the weak field on the left, there are fewer field lines penetrating that surface than there are with a field on the right. We would expect then that there should be a direct relationship between the flux of a field and the field strength. In this case here, we're talking about the electric field strength. Okay, the greater the field strength, the greater the number of electric field lines that will penetrate the surface. I should say penetrate a given surface. And finally, this last factor is probably the slightly more complicated one, and that is, what about the orientation of the surface in that field? So let's start by taking a look at a uniform field here, and we're going to look at three different surface orientations. Same surface, okay, of the same area, but oriented in the field slightly differently. In the first case, we'll look at having the surface oriented in this fashion so that it is really perpendicular to the field itself. And take a look at how many field lines penetrate that surface. What if we rotate that surface slightly, maybe at a 45-degree angle, so that it looks like this? Do you see that even though the surface area is exactly the same, the field strength is exactly the same, fewer field lines penetrate that second surface, the surface oriented at an angle, than they did in the first surface. If I want to look at an extreme here, what if I orient the surface like this? For a two-dimensional surface here, okay, in this case here, there is no flux, right? There are no field lines that penetrate that two-dimensional surface. So how can we state this here? Well, qualitatively, we can say that the flux will be a maximum when the surface is perpendicular to the electric field. The flux will be a minimum, really zero, when the surface is parallel to the field. We'll see how we can express this mathematically, okay, these same ideas, very shortly. We saw in the previous slide that the area of a given surface directly affects the flux through it. That is the number of field lines that can penetrate the surface. So to deal with the concept of flux in the most general way, we're going to introduce the concept of an area vector, having both magnitude and direction. We'll start with the simplest case of a flat surface, then extend our reasoning to the more general case of curved surfaces. So for a flat surface, we introduce the area vector A, where the magnitude of that area vector A represents the area of the surface as we might expect. The direction of A is always perpendicular to the surface. And if the surface happens to be closed, okay, then the vector A points outwards, away from the surface interior. So for example, for this closed surface here, this cubical surface, okay, the area vector describing each of the faces, okay, at least the faces we can see here, maybe not the back face, I can't show that. Okay, the area vector for those faces represents an outward pointing vector, okay, away from the surface interior. So how do we represent the area vector for a closed surface? As you might expect, we look at an infinitesimally small piece of the surface, okay, a piece so small that we can consider it to be flat. And we call this infinitesimally small area vector dA, okay, where the magnitude of dA, okay, the magnitude of that infinitesimal area vector, okay, represents the area of that infinitesimal surface element. Okay, a surface element that is so small it can be considered to be flat, okay, such that dA has a unique direction. And you know, to make sense of this, let's consider the Earth, okay, a curved closed surface that we're very familiar with. When looking at, let's say, the floor of a classroom that you're in, or the floor of your house, which really represents a very small piece of the entire Earth, you would consider it to be flat, even though technically it has a very slight curvature to it. So you kind of see that, you know, when we look at a classic projectile, for example, we're considering a small enough piece of the Earth that the surface is flat. Okay. In the same way here, if you look at a small enough piece of a curved surface, you can consider it to be flat, in which case that area vector dA is really no different than the area vector A for a flat surface. When we sum up all of the dAs for the entire surface, okay, in other words, in the language of calculus, take the integral over the entire surface of all those infinitesimal area vectors, well, as you would expect, we get the area of the entire surface. All right. As for the case of flat surfaces, okay, the infinitesimal surface element dA is always perpendicular to the infinitesimal, okay, surface element. Okay, nothing new there. And we would expect that it always points outwards for a closed surface. Again, really nothing new there. So we've talked qualitatively about the meaning of electric flux, saying that the electric flux is a measure of the number of field lines or the amount of field that penetrates a given surface. But how do we calculate it in a quantitative way? We'll start by considering the simple case where the electric field is uniform, okay, over a given surface. So notice here we've got this flat blue surface. Notice that we have a uniform electric field, okay, uniform in both magnitude and direction over that surface. Notice that this red area vector A, as we said previously, okay, the magnitude describing the area of the surface, okay, by definition, the direction of that area vector is always perpendicular to the surface. So here we see that the angle made between the area vector A and the electric field E, okay, that single angle has a value theta. So how do we define the electric flux for this uniform electric field. We do it as such. We define the electric flux to be the dot product of the electric field in that area vector A. And remember that the dot product is a scalar product, okay, giving you a value that is a number or scalar. And by definition of the dot product, when we take the dot operation of these two vectors, this one form of vector multiplication, it is equal to the magnitude of, okay, the first vector, in this case the electric field vector, times the magnitude of the second vector, that would represent the area of the surface, times the cosine of the angle between these two vectors. So here, just to specify this, be very clear, E represents the uniform electric field at the surface, A the area vector, which we've defined previously, theta the angle between these two vectors, E and A. And we'll get an idea in some upcoming slides about this cosine theta factor and how that can be used to take into account the orientation of the surface with respect to the field. Okay, one other thing we need to talk about that's very important is the concept of net flux. When we talk about the net flux through a closed surface, in the case I'm showing you here in the diagram, for this uniform electric field, the electric field lines go in a single direction and penetrate the surface in a single way. For a closed surface, it is possible to have electric field lines both entering that surface and leaving that surface. Okay, in which case we would define the net flux for that closed surface to be the difference between the number of field lines leaving the surface and the number of field lines entering the surface. Okay, we'll see later how this concept applies when we talk more formally about Gauss's law. All right, so in the previous example, we considered the flux of a uniform electric field through a single flat surface. In this slide, we'll consider a slightly more complicated case, that of a uniform electric field through a closed surface. So the problem goes something like this. I'm showing you the picture here of the uniform field. Okay, we have this cubical surface here. Notice the orientation of the field with respect to the cubical surface. The uniform electric field is directed in the positive x direction and has a magnitude E. We're told that this cubical surface, each side has a length or dimension A. So how do we find the total or net electric flux through that closed surface? Start here by noting that the area of each cube face is A squared. Okay, this surface has 6 sides, each with the same area A squared. And that when we represent each of these sides with an area vector A, which must be an outward pointing area vector, okay, for a closed surface. And I'm showing you here these 6 area vectors here. Notice that those area vectors are normal to each, perpendicular to each of the 6 faces, and point outwards. For a uniform field, okay, we said that the flux through the surface is given by the magnitude of the field times the magnitude of the area of that surface times the cosine of theta. Okay, really here, if we want to find the net or total flux through this closed surface, we must consider the flux through each piece of the surface. And really, this is, like we said, is a cube. It consists of 6 sides, so we can separately calculate the flux through the top side, the bottom side, the front side, the back side, the left side, and the right side. Okay. Note here that the flux through the top, bottom, front, and back is 0. Why? Because when you look at the diagram here, for each of those surfaces, the electric field is perpendicular to the area vector A. And thinking about this qualitatively, What does flux measure? Flux is a measure of the amount of field, the number of field lines penetrating a surface. When you look at the top surface, the bottom surface, the front surface, and the back surface, okay, there are no field lines that penetrate those four surfaces, those four sides of this cube, in which case the flux through those sides is all zero. Okay, mathematically speaking, you would find that when you take the cosine of theta, the angle between the electric field E and the area vector A, that the angle would be 90 degrees and the cosine of 90 would be 0. So the only two sides we really need to consider, and you can see it in the diagram, are the left side and the right side. Starting with the left side, using our definition of electric flux, magnitude of E times magnitude of A times the cosine of theta, the magnitude of the electric field is given by just E. The magnitude of the area vector A, just the area of each side, is A squared. In this case here, be careful, notice that the electric field is directed in the positive x direction to the right here, let's say, but notice for the left side of the cube, the area vector is directed left. In other words, the angle between these two vectors is 180 degrees, in which case the flux through the left-hand side of that cube is minus E times A squared. When we similarly take a look at the flux through the right-hand face here, okay, over here, in this case here, we see that the electric field and the area vector A point in the same direction, in which case we're taking the cosine of 0 degrees. Okay, the angle between these two vectors being 0 degrees, in which case, okay, the flux is just positive E times A squared. So when we actually find the net flux through all six faces, okay, adding up 0 plus 0 plus 0 plus 0 minus EA squared plus EA squared, we get 0. Okay, we find then that the total flux through that cube is 0. I want to point out something here that, okay, for a closed surface, when field lines enter the surface, the flux is negative. So for the left-hand side of this cube, okay, where field lines were entering the surface, okay, that gave us a negative value for flux, minus EA squared. When field lines leave the surface, and that would, in this case, be for the right-hand face, okay, notice there that the flux was positive. It was greater than 0. So this is a general rule here. Something else that we can conclude or infer from this problem, which is really a precursor to understanding Gauss's law. It will make a lot more sense later, but the result we can glean here from this problem, the fact that the total flux through the surface is 0, is consistent with Gauss's law, as we'll find out. For any closed surface that contains no charge inside, okay, no net charge inside, the net flux through the surface will be 0, as we will see when we formally state Gauss's law. So we just looked at how to quantitatively calculate the flux of the electric field through a surface when the field was uniform over that surface, or at least piecewise uniform over the surface, as was the case in the previous problem we looked at with the flux of a uniform electric field through a cube. Recall that while the field was constant in magnitude, the field was not constant in direction over each face of that cube, okay? In which case that could have created a problem for us. But for any individual cube face, and there were 6 of them, we could say that the electric field was constant in both magnitude and direction over any single face, in which case we calculated the flux through each face separately, added up those fluxes to determine the entire flux through the cube. Okay, but how do we calculate the electric flux when the electric field is not uniform over a given surface? okay, either because the magnitude of the electric field changes over the surface and or because the direction of the electric field changes over the surface. So this is where calculus comes in to save the day, okay, calculus to the rescue. Is you would now probably expect we need to visit the land of the infinitesimal. So what do we do when the electric field is not uniform over a given surface, either because the magnitude and or direction of the electric field changes? We consider an infinitesimal surface element, okay, a piece of that surface so small, okay, that we can consider the electric field to be uniform over that infinitesimally small surface element. That infinitesimally small surface element, okay, represented by this little red piece in the diagram here, as we've said previously, can be represented by an infinitesimal area element, dA, okay, a piece that is so small we can consider it to be essentially flat, such that the area vector dA is perpendicular to the entire surface. So remember that if that surface is curved, we look at a small enough piece so that we can consider it to be flat. So in that case, okay, not only is that area vector going to be constant, but in that case, being such a small surface element, the electric field will be constant as well. So, okay, for this, we can define the electric flux through that infinitesimally small surface element, okay, to be d phi. If big phi sub e represents the flux through a uniform surface, okay, then in the language of the infinitesimal, d phi sub e should represent the electric flux through an infinitesimal surface element, dA, okay, and we would calculate that infinitesimal electric flux, that is the flux through an infinitesimal surface element, simply to be the dot product of E and dA, okay, that infinitesimal area element. If we want to calculate the total flux through the surface, okay, well, again, using the concept of calculus, what do? We simply sum up all of the infinitesimal fluxes through each piece, okay, which amounts to, in the language of calculus, taking the surface integral, okay, over that entire surface of E dot dA. So, how do we actually do this in practice? We will talk about in great detail in our next lecture. Okay, but here we can say that the total flux through a surface, okay, that can be curved, a surface where the electric field may not be uniform over that surface, can be found by taking the surface integral of the dot product of E and this infinitesimal area element dA. So now that we've talked about how to calculate the flux of the electric field through a surface, we're ready to introduce Gauss's law, one of the 4 fundamental laws of electromagnetism. So let's start with a qualitative statement of it. Gauss's law tells us that the net electric flux through any closed surface, and remember when we talk about the net flux, we're talking about the difference between the number of field lines leaving the surface, okay, and those entering the surface. So the net electric flux through any closed surface is directly proportional to the charge enclosed by that surface. Now, qualitatively speaking, this should make sense. Think about the example of the cube that we looked at previously, where there was no charge enclosed by that surface. And in that case, we saw that the net flux was 0. Why? Because for every electric field line that entered the surface, there had to be one field line that left the surface, okay, giving us no net flux. Now, if charge happened to be enclosed by that surface, and we did not look at this case, then the net flux would not be 0. If it was a positive charge that was enclosed by the surface, okay, I should say a net positive charge, we would infer that more field lines would leave the surface than enter it. Why? Because we know that electric field lines start on positive charges and leave them. Whereas for the case of a net negative charge enclosed by the surface, the opposite would be true. we would infer that there would be more field lines entering the surface than leaving it.
So let's take a look at applying Gauss's law to a fairly simple example to see the correlation between the flux through a surface and the charge enclosed by the surface. So in this example, we're asked to consider once again the electric dipole. Notice here that the electric field lines are drawn for the dipole configuration. And we're asked to verify Gauss's law for each of the surfaces shown. So right now there are no surfaces shown, but they will appear in time. So let's start by taking a look at this green square. That will be our first surface that we consider. When we calculate the net flux through that surface, we need to take a look at the number of field lines that leave the surface, okay, and then subtract the number of field lines that enter the surface to get the net flux. When you look at this, we see that 10 field lines leave the square, no field lines enter it. That would give us a net flux of positive 10. When we actually measure the charge enclosed by the surface, we see that the charge enclosed is plus Q. Now, the next surface we'll consider is this pink octagon. Okay, for the pink octagon, when we calculate the net flux, we see that in this case there are no field lines leaving it, but 10 field lines entering it. This corresponds to a net flux of negative 10. This is where we can use Gauss's law to make a prediction of the charge enclosed by the surface. If we said above that a net flux of positive 10 corresponded to a charge enclosed of plus Q, we can then reason that a net flux of minus 10 should correspond to a charge enclosed of minus Q. And indeed, when we make the measurement or simply look at the picture, we see that yes, the charge enclosed is minus Q. For the red rectangle here, we see that when we examine the number of field lines entering and leaving the surface, we see that 2 field lines leave it and 2 field lines enter it. This corresponds to a net flux of 0. According to Gauss's law, the net flux through that surface should be proportional to the charge enclosed. And so if the net flux is 0, we would expect there should be no charge enclosed by that surface. And indeed, when we make the measurement there, when we look inside of that red box, we do see that yes, Gauss's law is correct, that there is no charge enclosed by that surface. For the black oval we see here, this oval circumscribes both of the charges, plus Q and minus Q. When we calculate the net flux, we see that 5 field lines leave that black oval and 5 field lines enter it, giving us a net flux of 0. So once again, we would predict, according to Gauss's law, since the net flux is proportional to the charge enclosed, a net flux of 0 should mean that there is no net charge enclosed by that surface. And indeed, when we make our measurement, we see that the charges plus Q and the charge minus Q will cancel each other out, okay, to give us 0 net charge enclosed. And finally, if we look at this purple circle here, we see that this is really no different than the case of the pink octagon, that in that case 10 field lines enter the surface, no field lines leave it, okay, giving us a net flux of negative 10. Okay, and based on the problems we've looked at previously, okay, a net flux of negative 10 should correspond to a charge enclosed of minus Q, which when we take a look is indeed the case. So once again, we see Gauss's law in action, that the net flux through a given surface is proportional, directly proportional to the charge enclosed by that surface. So notice here when we compare the pink octagon to the purple circle, that the net flux through both of those surfaces is exactly the same, okay, suggesting that the flux is independent of the surface shape.
Alright folks, we're going to take a look at a simulation here to try to help us understand this electric field line model, sometimes called the line of force model. What you see here in the middle of the black screen is a dot. Right now, and that dot represents a charge. Right now there is no charge on that small spherical object, but we will now put a charge on it. As you see here, where the cursor is, it now has a positive 1 microcoulomb charge. Take a look, according to our electric field line model, the lines of force or field lines emanate from that positive charge and move outwards towards infinity. Take a look at what happens if I double the charge according to our model. Okay, I go from 1 microcoulombs to 2 microcoulombs. We double the number of field lines. If we want to now make the charge negative, let's see what happens if we start out here with a minus 1 microcoulomb charge. When we put in those field lines, you'll notice that once again we are representing a charge of 1 microcoulomb with 6 field lines. The fact that it's negative shows us that the field lines go towards this negative charge. If we double the amount of negative charge here, we go from minus 1 to minus 2 microcoulombs. Once again, you see here the effect upon the field lines. We should double the number of field lines. Now in our simulation, we are going to shift from the concept of field to that of flux. In order to talk about the electric flux, we need to introduce a surface, and that's what I'm doing here. You see here I am introducing this red surface, and you will notice here that the flux represented with a symbol phi is shown in this box right here. So we're going to change this. We're going to start with a charge of 1 microcoulomb here. And remember that the electric flux through a surface is a measure of the number of field lines, the number of electric field lines, or the amount of field that actually penetrates that surface. Take a look here. For a charge of 1 microcoulomb enclosed by that surface, the flux is about 1.13 times 10 to the 5th. Okay, if we double the amount of charge enclosed, see what happens to the flux. Notice that the flux doubles. We have twice as many field lines penetrating that surface. Notice that if I change the shape of the surface, taking a look at the flux box, it does not affect the flux at all. Okay, and we see that the shape of the surface is independent of the flux. The only thing that affects the flux is the amount of charge enclosed by the surface. Now let's see what happens if we change the sign of the charge enclosed. Okay, notice that when we have a positive charge enclosed, the flux is positive. That is, okay, more field lines leave the surface than enter. Okay, if our charge goes to, let's say, negative 1 microcoulombs, notice now that we have more field lines entering the surface than leaving, so our flux is negative. Okay, once again, if we double the charge enclosed, we go from minus 1 to minus 2 microcoulombs. Okay, we are going to double the flux through that surface. Once again, the flux being negative. Alright, so now let's see what happens if we move our surface here. I'm going to go back to a positive flux here. So we have 2 microcoulombs where the flux through our yellow surface is about 2.26 times 10 to the 5th SI units. Watch what happens if I pick up this surface and I move it over here so that there is no charge enclosed by it. Okay, notice that the flux goes to 0. Okay, I can move this around to different locations and we see that the flux remains 0. Okay, only if there's actually charge enclosed by that surface do we have a net flux through it. Alright, and while we're at it, let's take a look at changing our charge configuration. We're going to go from a single charge to a charge configuration consisting of two charges. Notice that this is a dipole configuration. And in terms of electric field, oh, I'm sorry, it's not a dipole. Our one charge is 2 microcoulombs, the other is -3. Let's make it a dipole configuration here. So how about we look at one charge being 2 microcoulombs, the other being -2 microcoulombs. You'll notice that we have the same number of field lines that leave our positive charge as enter our negative charge. Once again, notice that the flux through the yellow surface right here is 0 because there's no charge enclosed by it. If I move this surface, if I move it so that it encloses the positive charge, we now have a positive flux as we have field lines leaving it. Okay, more field lines leaving than entering. Notice that if we move this yellow surface over here so that it encloses the negative charge, okay, if it encloses the negative charge here, that now our flux here is negative. And let's look at one more thing. Let's look at what happens if we extend the surface so that it encloses 0 net charge. In that case, you'll see here, looking at this flux box, that because there is no net charge enclosed, the net flux is 0. In other words, we have as many electric field lines entering that surface as leaving it.
So let's quickly review the factors that affected the electric flux in the simulation we just witnessed. Starting with changing the shape of the surface. As you recall, when we change the shape of the surface, so long as we didn't change the amount of charge enclosed, this had absolutely no effect on the flux. Changing the shape of the surface does not affect the number of field lines that penetrate it. Changing the magnitude of the charge enclosed within the surface certainly changed the flux through the surface. We saw in our simulation that when we doubled the charge enclosed, we doubled the flux through the surface. Changing the sign of the charge enclosed also changed the sign of the flux. When electric field lines leave the surface, okay, that is when we have a positive charge enclosed. The flux is positive, okay, whenever we have more field lines leaving than entering. When we had a negative charge enclosed by the surface, we saw that the flux, the net flux, was negative. That's because more field lines enter the surface than leave it.
Thus far, we've considered the meaning of Gauss's law in a qualitative sort of way, by simply counting field lines to give us a measure of flux. Let's now use our quantitative description of electric flux to arrive at a quantitative statement of Gauss's law. So, starting with, or simply reviewing the meaning of the net electric flux through a closed surface, we're saying that it is a quantitative measure of the amount of electric field penetrating the closed surface. And how do we measure the amount of electric field? Okay, by looking at the number of field lines. So we can alternatively say that, okay, the net electric flux through a closed surface is a measure of the net or total number of electric field lines penetrating the closed surface. And remember, we've got to take a look at both field lines entering the surface as well as leaving the surface. We said that Gauss's law tells us, or really is a statement about the relationship between the net electric flux through a closed surface and the charge enclosed by the surface. And we said that there is a direct relationship, okay, that the net electric flux to the closed surface is directly proportional to the charge enclosed by the surface. Okay, now using our definition, our quantitative definition of electric flux that we talked about previously, on the left-hand side here we see, okay, our flux integral. Just a couple things to point out. Okay, this surface integral, this dot product of the vectors E and dA, Okay, remember E, the electric field, dA, that infinitesimal surface area element, okay, on our closed surface. And want to be very specific here. When we look at the meaning of this the meaning of this integral here, first of all, we notice that it is a surface integral. Okay, and this little circle here tells us that it is over a closed surface. We're integrating over a closed surface. Gauss's law only applies to the case where you are dealing with the flux through a closed surface. Thus far, our statement of Gauss's law is in the form of a relation, not an equation. So to turn a relation into an equation, we need to introduce a proportionality constant and to then somehow find its value. So we can use what we know about Coulomb's law to accomplish this. That is, to find the value of the proportionality constant. Why? Because we can look at a specific case of a charge distribution. For simplicity, we're just going to look at a point charge, KQ, and we can choose a specific Gaussian surface. And for simplicity, okay, because of the symmetry, we will choose a spherical Gaussian surface I'm showing you here in yellow. And because we know what the electric field looks like for a point charge, okay, notice the radial symmetry of these field lines, okay, we can then use this fact that we know what that electric field looks like independently of Gauss's law. Okay, we determine this through Coulomb's law, so we can use this then to find the value of that proportionality constant. So what we're going to do then is we're going to use Gauss's law and to calculate the net electric flux through the closed surface using our definition of net electric flux, that is using our surface integral. So just a couple things here. Our Gaussian surface has a radius big R. We're going to look at an infinitesimal surface element I'm showing you here in red, and although it doesn't look so infinitesimal, use a little imagination. Remember that this infinitesimal surface element, okay, can be represented by this vector dA. It is so small that for this spherical surface, it is such a small piece of it, it can be considered flat. Remember the vector dA, the magnitude represents the area of that infinitesimal surface area. The direction of dA is an outward pointing normal. And because the vector dA is perpendicular to the surface, okay, notice that the vector dA points radially outwards in the same direction as the electric field over that small surface element. So we're going to now calculate the net electric flux through the surface. Okay, here is our quantitative definition of net electric flux written as a surface integral, okay, over that closed surface, and we can turn the vector product, okay, using the cosine theta, we can write it as a scalar here. Remember that the dot product is a scalar product. So as I said previously, note that the vector dA is parallel to the electric field vector E at all points on any surface element we can choose, okay, due to the radial symmetry of, okay, our charge distribution here. In which case, okay, when we look at the angle, the cosine theta factor, the angle between these two vectors, it's always 0 degrees for any surface element on that surface. Okay, we're taking the cosine of 0 degrees. And now what we're going to do next, you're going to be doing many, many times in the future when we learn how to apply Gauss's law. What you will notice is that, okay, for any surface element you could draw on that surface, Gaussian surface having a radius r, the electric field is constant in magnitude over that entire surface. In other words, the electric field at a fixed distance r from a point charge always has the same magnitude. What does that mean? That means that because the magnitude of the electric field is constant over that surface, it can be taken out of the surface integral. Okay, and when we choose surfaces in the future, when we apply Gauss's law, we will choose surfaces such that this criteria is always met, so that the electric field will always be constant over our surface, in which case it could be taken out of the integral. So why do we do that? Well, now take a look at what we've reduced the surface integral to. As we said previously, when you add up all of those infinitesimal area elements dA over the entire surface, all you're doing is getting the total area of the surface. And for our chosen Gaussian sphere of radius r, the surface area of that is 4 pi r squared. So as you will find, the calculus, may seem intimidating at first, but what we've done here when we've applied Gauss's law, we will always reduce that flux integral, okay, to a very simple expression where you are simply finding the surface area of your chosen Gaussian surface. Okay, no calculus required to do that. So we have an expression here for the net electric flux through that surface in terms of this electric field E. Now, in the future, we're going to want to use Gauss's law to determine E. Okay, but we already know the value of E for this particular charge distribution because we've figured that out by applying Coulomb's law. So that's what we're now going to do. We know that the electric field for a point charge is given by this Coulomb constant K, which we could also write in terms of these Gaussian units as 1 over 4 pi epsilon naught, K times Q, the charge of the point charge, divided by r squared. That is the expression for the electric field of a point charge. Okay, so when we substitute that in to our expression for electric flux, okay, when we substitute the expression for the electric field, okay, for the electric flux, notice that little r becomes big R because this is the electric field at the surface, okay, of our Gaussian sphere of radius big R. We plug that in here, and when we simplify, notice that the 4 pi r squared in the numerator cancels the 4 pi r squared in the denominator, giving us this very simple expression for electric flux. So the net electric flux through that chosen Gaussian surface is simply the charge enclosed Q, okay, divided by this proportionality, universal constant epsilon naught. So now all we have to do is find the proportionality constant in Gauss's law. Okay, remember, Gauss's law tells us that the net electric flux is proportional to the charge enclosed. We can say that the net electric flux, which we found to be Q over epsilon naught, is equal to some proportionality constant times the charge enclosed, which for this case is Q, in which case that proportionality constant has a value of 1 over epsilon naught. So now we can turn our expression for Gauss's law written as a relation into an equation, since we know this proportionality constant. And we come up with our formal expression of Gauss's law. Okay, the net electric flux through a closed Gaussian surface, that's on the left-hand side, is equal to the charge enclosed by that Gaussian surface divided by this proportionality constant epsilon naught here. So, okay, I will say this, you don't need to worry about this too much now, but this derivation of Gauss's law from Coulomb's law is valid for electric fields produced by static electric charges. Okay, we're going to see later on in the course, okay, the last 1/3 of our Physics 103, that electric fields can also be produced by changing magnetic fields. Okay, sounds a little weird, but electric fields can be produced by static electric charges or by changing electric fields. And what's interesting is that Coulomb's law cannot be used to describe such electric fields, but Gauss's law can. Gauss's law holds for electric fields produced by either static electric charges or by changing magnetic fields. So in this sense, Gauss's law is truly more general than Coulomb's law. Okay, and hence, we say that it is one of the 4 fundamental laws of electromagnetism. So more on that later in the course. Okay, what's more important for what we're doing now? We now have a quantitative statement of Gauss's law. Okay, in our next lecture, okay, we're going to talk more specifically about how we can apply Gauss's law to be able to calculate the electric fields for various charge distributions.